of the thing. The magnetic field through it times the area. Okay. Well, the magnetic field is related to the current in this coil, in the solenoid. Okay. So E2 mu naught N1, the number of turns per coil, times I1 times A2. The only thing that is changing, of course, is the current in coil 1. So minus mu naught N1 I1, N1 A2 d by dt I1. And let me write down the expression for the mutual inductance is minus M12 di1 dt. So if you compare these two expressions, you can see that mutual inductance is that. So in this case, we are able to come up with an expression for mutual inductance. And that was for perpendicular case. Well, if it was at an angle, you would have to involve the angle there. Okay. So M12 is mu naught N1 A2. And we can put in these numbers. So it's mu naught. All right, let me. Mu naught is 4 pi times 10. And it has 600 turns, and the length is 0.55 meters. And the area of the secondary coil is that. Centimeter squared, 10 minus 4 meters squared. Okay. That's 10 minus 11. We'll make it 10 minus 9. Okay. And this will be Henry's 4 pi times 6 times 1.1 times 1.4. So 211 nanohenries. Again, what the mutual Henry tells you is how large of an EMF is induced in this coil when the current changes in this coil. Okay? So that's what that is. A solenoid 50 centimeters long is wound with 500 turns. A wire. The cross-sectional area of the coil is 2 centimeters square. What is the self-inductance of the solenoid? So this is air filled, and L is mu naught N square A by L, A times L. So let's here's the expression. Mu naught is 4 pi times N is 500 divided by 0.5 meters square. Area of cross section is 2 centimeters square. So one of these cancels. Yeah. So that's 10 to the minus 11, and then we'll grab 4 of these. So we'll grab 5 of these. And this cancels with that. 25, one of them cancels, and that's 5. 11 minus 5 is 6 henries. Okay, so 126 microhenries. Along, do you have a question? Along cylindrical solenoid with 100 turns per centimeter has a radius of 1.5 centimeters, neglecting end effects. So what there's end effects is if you have solenoids, the magnetic field is like that, and then you'll get magnetic fields. Yeah. So there is some energy here outside the solenoid. The expression that you see for the magnetic field, this expression B equal to mu naught N I, that expression is for the field inside here. Okay, that's the strong uniform field. So there is some leakage of magnetic field. I mean, there is some magnetic field outside. Okay, so we're neglecting these guys. Neglecting end effects. What is the self-inductance per unit length of the solenoid? So and what they're asking is, what is the self-inductance per unit length? L divided by L is mu naught N squared A. Mu naught is 4 pi times 10 to the minus 7 Tesla. And N is 100 turns divided by 100 turns per centimeter. 1 centimeter is 10 to the minus 2 meters. Okay, so it's got 10,000 turns per meter. So solenoid this length has 10,000 turns of wire. and pi r squared, 1.5 10 minus 7, 10 minus 11, and this is 10 to the 4. So 10 to the 7. And there's a pi there, into pi. Henry per meter. This is henries per meter. Okay, so that's every meter of that solenoid has 9 microhenries of inductance to it. At the instant a current of 0.2 amps is flowing through a coil of wire, the energy stored in its magnetic field is that much. What is the self-inductance of the coil? The energy stored is given by 1/2 Li square. So L is twice the energy divided by I square. And so joules divided by ampere square is a Henry. Okay, so this is 2 times 10 to the minus 1, 4 times 10 to the minus 2, and then so 3 times 10 to the minus 0.3 Henry. How long after switch S1 is thrown does it take the current in the circuit shown to reach half its maximum value? Express your terms in terms of the time constant of the circuit. Okay, so when you close the switch, the current as a function of time is given by, this is the asymptotic value of the current, which is, as if this guy was not present, this is the final steady state value of the current, and then 1 minus e to the power of minus t over tau, where the time constant is L over R. Okay, they're asking you at what time will this be? At t equal to infinity, this term is 0. That's the maximum value of the current. So IT half is half the maximum value, equal to E over R. Okay, let me write it this way. Okay, you want the time at which it's half the maximum value. 1 minus e to the power t half over tau. Okay. So this cancels. Half equal to 1 minus e. And log 2 is 0.69. Okay, so this is 0.69. At 70% of the time constant, you get half the maximum value. The current in the RL circuit shown below reaches half its maximum value in 1.575 milliseconds. So we just calculated that. After the switch is thrown, determine the time constant of the circuit and the resistance of the circuit given this. Okay, so we will just use that expression. Okay. So the time constant is t half over log 2. So I don't have this formula on the formula sheet, so you might have to memorize that. So the time constant is 2.5 milliseconds. And then part B, the time constant is L over R. The millis cancel, and henries over second is ohms. So it's roughly 100 ohms. Yeah, so the resistance in this circuit is 99 ohms. Okay, we won't worry about this problem. It's too long. What is the self-inductance of an LC circuit that oscillates at 60 Hertz when the capacitance is 10 microfarads. So this is an oscillator circuit, and omega is equal to 1 over root of LC. Omega is 2 pi f. And this is given to be 60 hertz. Okay. So .7 Henries. So if this is 10 microfarad and this is 0.7 Henries, it'll oscillate at 60 hertz. And what it'll do is it'll pick up the the electromagnetic waves coming out of your socket. This thing will buzz. What resistance R must be connected in series with a 200 millihenry inductor of the resulting RLC circuit if the resulting RLC circuit is to decay to 50% its initial value of charge in 50 cycles to 0.1. Okay, so So the charge on this decays as it's oscillating, and here's the expression. Okay, so 50% of its initial value. So to get to 50% of its initial value, you just you want to make this half. Okay, so e to the power minus 200 millihenries. .28 ohms. Okay. All right, that finishes the problems.